Okay, so we continue with looking at MOSFET circuits under DC. In this lecture, we look at two different circuits for various values of resistances and voltages applied. So, like I did last time, what we'll do is I'll ask you to pause the video and solve at each point that you have to solve the circuit. Alright, so please try and do that. Alright, so these are the numbers, specifically the mu n Cox W by L is 4 milliamp per volts. This is what we'll use throughout this specific lecture. Alright, so this is the first circuit we look at. This is called a common source amplifier with source degeneration. You have probably seen this circuit for the bipolar transistor. So I'm sorry, this line is extra. It's okay. We are given everything. The VDD gate voltage, the drain resistance is 2 kilo ohms, and we are asked to find ID, VD, and VS. So right off the bat, please pause and solve this circuit. Okay, I continue. So the first step is to assume that the transistor is in saturation, and so we write the saturation region equation. So that is ID equal to mu n Cox W by L, which is 4 divided by 2, which is 2 into VGS minus VT the whole squared. VGS is VG minus VS minus VT the whole squared. VG is given, VT is given, so we get this. VS is not known, so we have two unknowns and one equation, and the other equation is the current equation for a current voltage relation for the source resistance. So you get Vs equal to RSID equal to 2ID. Now if you recall, we had solved these two equations last time in the circuit we had solved, which did not have RD. Alright, it was the same circuit except there was no RD. The drain was connected to 3 volts. So what we note here is that we get the same equations for this circuit with RD under the condition of saturation. Alright, if the transistor is in saturation, then the drain voltage does not appear in the equation, and therefore the equation remains the same whether there is a drain resistance or not. Alright, so this we had solved last time, so I'm not solving it again. You just look up last lecture. And what we had found was that the source voltage was 0.25 volts, ID was 0.125 milliamps, and the drain voltage was 2.75 volts. Alright, same answers. Now, of course, what is different is now we say, well, is this transistor in saturation given that RD is present? If RD is not present, then of course the drain voltage is 3 volts, gate is 0.9, the transistor is always in saturation. Now we have to check. So we say, okay, VD is 2.75, we check the saturation condition, is VG minus VT less than or equal to VD. VD is 2.75, 0.9 minus 0.4, which is less than 2.75. So yes, the answer is correct and the transistor is in saturation, and these are the numbers. So the drain current and the source voltage are the same in this circuit as the circuit without RD. Alright, it's an important recognition. But if we put RD, as long as the transistor stays in saturation, we keep increasing RD. As long as the transistor is in saturation, the drain current does not change. Of course, this is a property of the fact that the saturation current is independent of the drain voltage. Alright, now let us think about what happens as we increase RD. So RD here is 2 kilo ohms. The drain voltage is 2.75 volts. So now let us say we increase RD. Let's keep increasing RD. So as RD increases, the drop across RD increases. So VD decreases. So it keeps decreasing, and keeps decreasing until the point where the transistor goes out of saturation. So we have the condition here. So at what voltage does the transistor go out of saturation? When VD is 0.5 volts, right, from this condition. So up to 0.5 volts, if we keep increasing RD, the transistor stays in saturation. Okay, so for Vd equal to 0.5 volts, what must be the value of Rd? Vd is 0.2, it's not written here. Vd, I'm sorry, 0.5. So the drop across Rd is 2.5. The current is 0.125. So 2.5 divided by 0.125, which is 20 kilo ohms. Alright, so as you vary Rd from 0 to 20 kilo ohms, the transistor will stay in saturation, the drain voltage will keep changing. Okay, so the next circuit we solve is for Rd greater than 20, which is 24 kilo ohms. Alright, so now we already saw that the transistor will not be in saturation, and if we actually find Vd, it turns out to be 0, assuming saturation. So obviously the transistor is not. So now we must solve the circuit again, assuming that the transistor, in fact now knowing that the transistor is in the triode region. So I would like you to pause and solve the circuit with the transistor in the triode region. Alright, so we said, okay, I'm sorry, what is this? Oh gosh, yeah. Let me change this kW is, we don't want kilowatts here, we want kilo ohms. So, alright. So we say Rd is equal to 24 kilo ohms. And now we write the triode region equation and then substitute everything we know. So mu n C ox W by L is 4, Vg is 0.9, Vs, Vt is 0.4, Vd, Vs. So now we have three unknowns, Id, Vd, Vs. So we need two more equations. One comes from the source branch. We already saw that Vs is equal to 2 times Id. And the other comes from the drain branch. Alright, so is a Vd is equal to 3 minus 24 kilo ohms times Id. So of course Id is in milliamps here, as we've seen before. So we substitute these back in this equation and we solve for Id. Alright, I am going to let you do that. The derivation is here, but of course we'll not go through the derivation. It is just straightforward algebra. So of course we'll get a quadratic and we solve the quadratic and we'll get two values of Id. We have to determine which. In order to determine which, we find the Vs and the Vd. Alright, so Vs is either 0.22 or 0.19. Does that tell us anything? We don't know because both of them put the transistor in the on state, so that doesn't help. We look at Vd. So Vd is either 0.35 or 0.72. Only one of them will put the transistor in triode, as we've seen before. If both of them put it in triode, that means we made a calculation mistake. So in our case, 0.72 will put the transistor in saturation. As we already saw, Vd greater than 0.5 is saturation, and we know the transistor is in triode. So the correct answer is 0.35 volts. All right. Now here is a table of the two resistor values we just now studied. So for 2 kilo ohms, the drain current is 0.125. For 24, the drain current reduces. Why does it reduce? It reduces because the transistor went from saturation to triode, and the triode region current will always be smaller if the gate source voltage is the same, right? Now what is the gate source voltage? Let us see. So interestingly here, so the source voltage is 0.25. The source voltage has reduced. Why? Because the current has reduced. So the drop across the RS has reduced. So the gate source voltage in the triode region case is slightly larger. Alright. Nonetheless, for this circuit, the current will be smaller even although the gate source voltage is larger. Alright, and of course the drain voltage has reduced. Okay, so we discussed this already. So we go to the next circuit. So we replace the Rd with an NMOS transistor. Alright, so we have both NMOS transistors, and now we want to solve this circuit if Vg2, this gate voltage is 2 volts. Alright, so pause and solve. Basically find ID and VD given the gate voltages. Okay, let us see what to do. So as usual, what we say is, well, we don't know which transistor is in triode, which is in saturation. So let's assume both are in saturation. Okay, let me qualify that. VG2 is 2 volts. Do we know if M2 is in saturation? We actually do, because we know the gate and drain voltages. Gate voltage is 2 volts, drain is greater than the gate voltage. So of course M2 is in saturation. M1 we don't know, so we assume that M1 is in saturation and solve. Okay, how do we solve circuits that have two transistors? We write the drain current equations for both of them. Alright, very important. We write the drain current equations for both of them. So we assumed saturation. So if for M1 we say ID1 is all this, is 0.5 milliamps. For M2 we assume saturation and we get VGS2. Remember, Vs for M2 is not 0. It is in fact unknown, and because I've called that node voltage VD, I've written VD here. So we get this equation. Alright. So now we have VD, which is not a known quantity, but we know that these two currents are equal, and we have already found this current. So we equate this to 0.5 milliamps and solve for VD. And again there is a quadratic, so we get VD equal to 2.1 or 1.1. If VD is 2.1, VG is 2, not possible because that turns M2 off. So VD is 1.1 volt. Alright, so the answer is VD is 1.1 volt, which puts M1 in saturation, and therefore both the transistors are in saturation and the current is 0.5 milliamps. Okay, now some interesting analysis about this circuit. So we have two transistors and we have said that the VTs of the transistors are the same. The mu and Cox W by L of the transistor are the same. And if that is the case, and of course if the same current is flowing through both transistors, and if both the transistors are in saturation, then we can safely conclude that the VGS minus VT of both the transistors are equal, because everything else is equal. So the VGS minus VTs have to be equal. Alright. Now what that means is that when we are solving, assuming both transistors in saturation, we don't even need to write these equations. Why? Because we say, well, given all of this VGS has to be the same as this VGS, because the same current is flowing, assuming, and they are both in saturation. Same current is always flowing. But if you assume saturation, then this VGS has to be 0.9 volts. So if this VGS is 0.9, that means VD is 1.1 volt. Right? Has to be. And then we check if that 1.1 satisfies the saturation condition, as we did in the previous slide. Okay, so we really don't need to solve the circuit. So this solution we don't need to do. We directly can write that VD is 1.1 volt and then check if our assumption of saturation is correct or not. Alright. Okay, so that simplifies analysis sometimes if we are thinking as we solve. Okay, now I am asking the next question. So for Vg equal to 2 volts, we find that both the transistors are in saturation. Now I'm asking, what is the lowest and highest value of Vg2 for which M1 stays in, well, M1, M2 both stay in saturation. Alright, so let's think about it. As Vg2 is decreased, maybe I should write Vg2 here, no? Let me write Vg2 here, it is more kind of intuitive to be able to see the Vg2 there. So as Vg2 is decreased, 1 second, what happened? 1 second. As VG2 is decreased, as long as M1 stays in saturation, well, first of all, as VG2 is decreased, will decrease so that the VGS stays the same as 0.9 volts. And so VD will decrease. Therefore, if VD is decreased, at some point M1 will go into triode. What is that point? What is the VD at which M1 goes into triode? We've already seen 0.9 minus 0.4, so 0.5 volts. So our at Vg equal to 2, Vd is 1.1. So if we keep decreasing Vg2 up to Vd reaching 0.5 volts, M1 will stay in saturation. Alright, so Vd equal to 0.5 corresponds to Vg2 equal to 1.4 volts. Alright, so Vg2 equal to 1.4 volts. So from 2 we can go down to 1.4 and M1 will stay in saturation. And of course M2 is in saturation because we are reducing Vg2, M2 will stay in saturation. So that's the lower limit. The lower limit is 1.4 volts. If we increase Vg2, at some point M2 will go into triode because Vg minus Vt will become greater than Vd. What is that value? Vt is 0.4, so 3.4 volts. So Vg2 equal to 3.4, M2 will go into triode. Alright, so the range of Vg2 for which both the transistors stay in saturation is 1.4 to 3.4 volts. Alright, I'm sorry, this is 3.4. Yeah, this is 3.4. So 3.4 volts. Both transistors are in saturation. Okay. Okay, now let me do this 1 second. Okay, now so I'm drawing another conclusion. So as long as Vg2 is in this range, 1.4 to 3.4 volts, we say that both transistors are in saturation, and as we vary Vg, VGS2 and VGS1 will be both be equal to 0.9 volts. Therefore, VGS2 being Vg2 minus Vd will be 0.9, and therefore we can write Vd as Vg2 minus 0.9 volts. Alright, Vg2 minus Vd is 0.9, so Vd is Vg2 minus 0.9 volts, which means that delta Vd is equal to delta Vg2. Alright, so the derivative, right, or the delta. I mean, if I change Vd, Vg2 changes by the same amount, or vice versa. What is this circuit called? Where if I vary Vg, Vd will vary by the same amount as Vg. Or if I vary the input by a certain magnitude, the output would change by the same magnitude. The change in the output is the same as the change in the input. What is the circuit called? It's called a source follower. Source follower. It's a unity gain buffer, right? The output is equal to the input, the AC output, the change in the output. The DCs are different, but the ACs are equal. Alright. So this circuit in fact is a source follower circuit with the input at the gate of M2. Alright. And it works as a source follower in this range. Another one. Okay. 1.4 volts to 3.4 volts. Alright. That is the range. So this is important to recognize that whenever we build amplifiers, they have a DC range over which they work the way we expect them to work. Right? A source follower is expected to have the output delta equal to the input delta, and that happens only in this range, 1.4 volts to 3.4 volts. Each amplifier circuit has an input range over which that the amplifier works as an amplifier or whatever, a follower. Alright. And I say realistically this range is 1.4 volts to 3 volts, not 3.4, because if the VDD, this is the power supply that will be supplied to the entire system of which this source follower will be a part, and so the highest voltage typically in this system is going to be 3 volts. So although VG2 can go up to 3.4 volts, realistically it will never go to any voltage above 3 volts because everything else in the circuit is limited to 3 volts. Alright, next question. So this is a range 1.4 to 3 volts. Ideally, of course, I would like this voltage, the range of my input voltages over which this circuit works as a source follower. I would like that range to be 0 to 3 volts, but clearly that is not possible. But can I increase this range? 1.4 is rather just about 50%, right? Slightly larger than 50%. Can I increase this range? What can I do to make this range 1.4 to 3 volts larger? What can we do? Okay. So 1.4 of course was determined by M1 and it was determined by the fact that VD was 0.5 and then this is 0.9. Alright, so this 1.4 has two parts, the VGS plus this VD, alright, 0.5 plus 0.9. And of course VD is a function of VGS itself, which is 0.9. So if we want to reduce this 1.4, we have to reduce this 0.9 also, because this is 0.9 plus 0.5 and that 0.9 is the same as this 0.9. So if we reduce this 0.9, then we can get a higher range. Alright, what is the lowest we can make this VG1? Okay, I don't want to ask that question now. We'll ask it after 2-3 lectures. Right now, let us say that the lowest we'll make VG1 is 0.5 volts. Alright, that is the lowest we are going to be able to make. We'll see afterwards how this comes. And so VD then will be 0.5 minus 0.4 equal to 0.1. So the lowest that we can get for VG2 is 0.6 volts. Alright, so it was 1.4, so we can bring it down to 0.6 volts. So the highest range of VG2 we can obtain in this circuit is 0.6 volts to theoretically 3.4 volts, realistically 3.3 volts. Okay, next question. What do we lose when we reduce VG1 from 0.9 to 0. Okay, I'm making all kinds of silly, this is 0.5 volts. Alright, so what do we lose when we reduce VG1 from 0.9 volts to 0.5 volts? What do we lose? What do we lose? What we lose is the current, alright, because if the VGS is smaller, then the current that flows in this circuit is smaller. Of course, one can argue as to why that is called a loss, right? It's a good thing if the current is smaller, the power is smaller. So maybe lose is not the right word, but we'll leave it at that. Okay, let me say it. So the drain current becomes smaller. That is a consequence of VGS1 becoming smaller. The drain current becoming smaller, of course, makes the power consumption less. But as we'll see maybe after half a semester, the current smaller means the speed of the circuit becomes smaller also. So what we lose actually is speed, as we'll see much later. Okay, so how do we increase the drain current then? Suppose I want to make VG1 as 0.5 but I still want a larger current because I want a larger speed. What do? We increase the W by L. Alright, We increase the W by L of both the transistors, and everything else will remain the same. Alright, and of course the next question you should ask in your mind, but we will not address this today, is what is the impact of increasing W by L? What does that do to other performance parameters of the circuit? You think about it. I will not discuss it today, another time. Alright, let us now solve the circuit for VG2 equal to 1 volt. Alright, so this is 0.9. We said VG2 can go down to 1.4 for M1 to stay in saturation. So now we are making VG2 less than 1.4. So now we know that M1 is in triode. I'd like you to solve this circuit. We already know M1 is in triode, M2 is in saturation. So you just have to write the appropriate equations and solve them. So please pause the video and solve it. Okay. Alright, so we write the equations, M1 in triode, M2 in saturation, and the two currents are of course always equal. They are connected in series. So this is the triode region equation for M1, the saturation region equation for M2. The only unknown is VD, and so we can solve for VD. VD turns out to be 0.9 or 0.2 volts. 0.9 or 0.2 volts. VG2 is 1 volt. VD cannot be 0.9 because that will turn M2 off. So the correct answer is VD is 0.2 volts. And the corresponding ID, which we can find from any of these two equations, is 0.32 milliamps. So ID has reduced. It was 0.5 in saturation. Now of course it has to be smaller because the gate source voltage is the same. The transistor went from saturation to triode, so current has to reduce. Okay, let's make VG very high, 4 volts. Alright, we said that above 3.4 M2 will be in triode. So with VG equal to 4, M2 will be in triode, M1 will be in saturation. Reverse, so again we write the two current equations. Write them very carefully, that is the only thing. Please do this yourself and solve, and we'll get VD equal to 4.38 or 2.82. 4.3 or 2.8. Obviously this can't be 4.3 because VG2 is 4 because M2 will be off, and so we get 2.82, and that is the answer. ID is still 0.5 milliamps. This is interesting. Alright, this is interesting because M1 is in saturation. So the current in this circuit is not changed. It is still 0.5 milliamps. M2 is in triode, but it is carrying 0.5 milliamps. So it's going to have a much larger gate source voltage. Okay, let's see the gate source voltage. This is 4, this is 2.8. So the gate source voltage of M2 is about 1.2 volts. This is 0.9 volts. Alright, so a triode region transistor carrying this saturation current of another identical transistor, the triode region transistor must have a higher gate source voltage, 1.2 volts. Alright. Alright, so yeah, we said this already. Okay, the other thing to note here is that VD is floating, floating in the sense that VD adjusts itself to meet the conditions of both the transistors. Alright. Okay. Alright, next lecture we'll study more DC circuits, and then the lecture after that we'll start AC, small signal AC analysis.